There we go. This will be a video on section 4 of chapter 22. We're going to talk about the processes as a star runs out of oxygen. So let me go back to the screen, which I doesn't want to do. There we go. So we are having screen difficulty. There we go. What happens when a star's core runs out of hydrogen? The creation of a couple of new chemicals, and then planetary nebula and how they form. And we're going to talk about a couple of specific planetary nebula that I will want you to know some about. So, late life of a low mass star. The star is running out of hydrogen. So we start out with, 4 hydrogens, and through the proton-proton chain, they combine to 1 helium and energy is released. The helium is more massive, and the protons and neutrons in it are more densely packed than the hydrogen. So the core is becoming more massive. As this happens, the star evolves off the main sequence. So it has spent much of its life on the main sequence, HR diagram, we've looked at them before, and it will now spend time collecting hydrogen as the hydrogen runs out. There begins to be so much helium in the core that the star, the core actually is condensing slightly, and because of that, it is increasing in temperature, which increases the temperature of the bottom of the radiative zone and makes the outer layers of the star expand. So the star is getting larger because the radiative and convection zones are thicker. They have more space for temperatures to decrease, and so the outer edges of the star are actually lower in temperature because the core is hotter. Really kind of counterintuitive, so make sure and think about that. But the helium is collecting in the core, so pressure and temperature are increasing, and helium requires a much higher temperature to fuse. Helium fuses into carbon and nitrogen, and so carbon and oxygen. Helium fuses into carbon and oxygen. So it takes a long time for there to be enough helium in the core for it to get hot enough for fusion to start. When that happens, the helium starts fusing all in a flash, sort of reminiscent of the fact that as the protostar is contracting, suddenly the hydrogen fuses all in a flash. But that when that flash occurs, the internal structure of the star kind of jostles around, and for a short period of time, the radius decreases. So let's look at the times on this. Main sequence. Now this is for stars 2 solar masses or less. Main sequence, 11 billion years. That becomes a red giant, spends 1.3 billion years on that arc up and at the B phase. Hydrogen flash, and it takes 100 million years to drop back down. We're about to look at the chart again. And then another 20 million years in the second red giant phase. So as this occurs, we have hydrogen in the outer shell. And out here, it's not hot enough to fuse. It's just there. It's shining. Um, and then hydrogen that is fusing. It fuses into helium, and those helium molecules are more dense, so they get pulled more strongly by the gravitational pull of the star, and so they drop into the helium core, where, helium is just hanging out, but it's pulling down and then eventually ends up in a helium core shell where there's helium fusion occurring. And those helium are forming into carbon and oxygen. And so those are heavier still, and they will collect in this central core. When those, the temperature increases in each phase. And so as the second red giant phase, we have carbon and oxygen in the core, and it is collecting. Once we no longer have helium that can fuse into hydrogen and oxygen, the star basically at this point is in the dying stage, because the core is not fusing, and so there's not enough heat being pushed out to hold all the heavy layers of the star, and so it sort of does this bouncy thing where the outer layers try to collapse a little bit, but that doesn't work, so they bounce off the core and explode into a planetary nebula. So planetary nebula, definition: vaguely round nebula of hot gases from the explosion of a low-mass star. So this name was first used in the early 18th century when we were looking through telescopes, and from the distances that we were looking, this was simply just a bigger round dot than the regular stars. And so the association with planets, and so misleading name. I'm sorry. Names are hard. Lots of people say math is hard. No, names are hard. So we're going to look at a couple of specific ring of nebula. The Ring Nebula is probably the most famous nebula out there. M57, located 2,000 light years away in the constellation Lyra. It is approximately 1 light year in diameter. The central star, which is this one, about 120,000 Celsius, which also means 120,000 Kelvin. And we are more than likely looking down the barrel of the explosion rather than at the entire explosion. The blue region, very hot helium located close to the star. The red regions out here are ionized nitrogen. So super hot. That is the outermost regions of the star that have exploded off. And then they call it green. This pale teal, light blue, seafoam green region, that is oxygen emission, so intermediate temperature. So this explosion gets hotter as we go out. So what I want you to remember about Ring Nebula is that it is the most famous nebula out there, that is approximately 1 light year in diameter, and that we are probably not seeing the entire explosion. What they really look like is more like this. This is Rings of a Butterfly Nebula, so M2-9. 2,100 light years away in the constellation Ophiuchus. So for this one, the central star is part of a binary and has ejected mass in 2 different directions. We have this torus around the star that is stopping the explosion from coming in all 360 degrees. So it's only extending out two different directions. The colors tell us, the approximate temperatures. Neutral oxygen in red, once ionized nitrogen in green, twice ionized oxygen in blue. So, I'm not going to ask you to remember the colors or the chemicals, but I want you to remember what they look like, the name, the distance that they are away from us, and, sort of the fact that it's a star that exploded. This is a stellar outburst that occurred about 1200 years ago. We'll look at, I think, two more. Glowing Eye Nebula. So this one's named NGC 6751. So New General Catalog. So this is a list. A stellar catalog is a list of things in the night sky. Stars, nebula, black holes, all kinds of things. This one is 6,500 years ago, 6,500 light years away from us in Aquila, which also means that the light that we see right this minute is 6,500 years old. The blue regions are the hottest gas. The red and orange show locations of cooler gas. The reason I don't want you to remember the colors and what chemical they mean is because these images are created using different types of light, and so the colors are not unique. If I pulled up a different image of Glowing Eye Nebula, different images show these gases in different colors. So the color, while it's important to help us recognize the difference in the temperatures, does not just automatically, blue does not automatically mean helium. Green does not automatically mean hydrogen. So these cool streamers out here that are farther away from the star, we think that is due to stellar wind pushing them out from the star, but the central star in this case is about 140,000 Kelvin, and this entire structure is 600 times larger than the diameter of our entire solar system. So huge. This nebula, about 3 years ago, the name Gummy Bear Nebula was proposed for it. I don't believe that it has been classified as that yet, but I think it's kind of a cool name. So NGC 7027, 3,000 light years away in Cygnus. Several stages of mass loss. So this one's kind of interesting. The blue concentric rings out here show the very outer shell of the star that it shed as it expanded. So it expanded, and then as the collapse of the core started, the outer edges kept going while the central portion of the star collapsed just a little bit, and so it shed those layers in a fairly symmetric way. Then we have the two bulbs of an explosion. So we're probably looking at this edge on, actually diagonally. And so we have two bulbs of the explosion, which tells us that this would once again be a star in a binary, because the binary star is what prevented the explosion right along the equator. The central star here is sort of hard to see. So talking more about those shapes. We see lots of different shapes. Helix Nebula, which is called the Eye of God, is another great one that we're probably looking down the cone of the explosion.